Okay, hello everybody. I hope you can hear me. I think by my watch it's time to start. My name is Felipe Wisi. I'm from NEC Laboratories Europe in Germany. And today I'd like to tell you about a project we've been working on for a couple of years now called Unikraft, in which we're trying to build highly specialized POSIX compliant software stacks and make it easy to do so. So if you're in the embedded world, you have a choice between choosing a general purpose OS or an embedded OS. And if you choose a general purpose OS, they obviously have lots of great advantages. You can support lots of devices and applications. You have a very familiar development environment. And of course, they're POSIX compliant. On the downside, they're kind of hard to customize. If you're looking at Linux or FreeBSD, they're generally speaking monolithic kernels. I know there's kconfig, there's menus, you can do a bit of tweaking. But ultimately, if you're really trying to specialize your image or your OS, it might need lots of tricky engineering work, which an application programmer might not be interested in doing. It has lots of lines of code, so there's a large attack surface. You can have lots of exploits as a result. And because it's not specialized, maybe you have a large memory footprint, image sizes, memory consumption, and so forth. And of course, if you're in safety critical domains, certification might be a must. And usually speaking, the more lines of code that you have, the more expensive it is to certify something. And so these sort of general purpose OSs are usually a difficult proposition. Embedded OSs are sort of on the opposite side of the spectrum. They're very resource efficient and they have a smaller attack surface. They're cheaper to certify, but they're for the most part non-POSIX compliant. So it takes at least a significant amount of effort to port applications, and they can have an unfamiliar development environment. So you have to kind of make a choice. And the question is whether there couldn't be another alternative that sort of picks and chooses the best things from both sides. So if we were to design a new sort of OS, what would it look like? What would we need? So we would like to have easy configuration and customization, a minimal attack surface, low certification costs, easy to port and use existing applications. And we would like it to also be efficient and hopefully performant. And all of this seems to suggest that if we could somehow specialize our OS to the needs of particular applications, we could get most of these benefits. And this is especially what we're trying to do here. Imagine that you're targeting a single application. It could be an IoT gateway. It could be a web server. In this example, it's a web server. And you can imagine that you have the OS kernel, the libraries, third-party libraries. And to run the web server, you only need the colored boxes you have in there, but you have lots of libraries and other software that is running on your system that you don't really need. So it would be great to try to eliminate that and somehow automatically create a software stack, an OS that just caters to the needs of that web server. And that's what Unikraft is trying to do. So this is a sort of architecture diagram. The premise is that everything in Unikraft is a library, even OS primitives such as schedulers, memory allocators, network stacks. And that gives the ability to sort of more easily pick and choose how you build your stack in terms of what the application actually needs. Even things like platforms, what we call platforms, which are things like whether you're running on a Raspberry Pi or a Xilinx Ultra 96 or KVM as a virtual machine, those are also libraries, and so is architectural code, whether it's x86, 64, ARM64. All of this is customizable via kconfig type menu. So you can if you want, you can pick and choose easily which of these libraries you want or you need. We've added a fair amount of different language support in order to be more attractive to people who might potentially use it. So there's compiled languages such as C, C++, and Go, and interpreted languages such as Python, Ruby, or WebAssembly. We're trying to be as much as possible POSIX compliant so that it makes it easy to use existing applications. We have tools for easy porting and lots of documentation on how to have existing applications run on Unikraft. In addition, we already have built in the ability to run certain standard applications such as Nginx, SQLite, and Redis. And as I mentioned earlier, we can support multiple what we call platforms. In this talk, it's mostly about bare metal and running on ARM64 devices, but we also support the ability to run on virtual machines on different hypervisors. Okay, in terms of security features, I already mentioned that we have one of the targets is to have a small attack vector because we are specializing. But we also would like to prevent other common attacks because we're coming from what's called the unikernel world. And there was a paper a few years back basically saying that, yeah, unikernels are great because they're specialized, they have a small attack surface, but they largely ignore standard protection mechanisms that general purpose OSs have. So in Unikraft, we're in the process of adding things like ASLR, stack canaries, page protection bits, and heap integrity checks. And we want to also make sure that we have features such as a secure memory allocator, and in cases where it's needed, we can, because we're running at the OS level, of course, we can make use of direct privilege functionality at lower performance. So just to give you a little taste of things, here's a quick demo of Unikraft running on a Raspberry Pi 3. What we have is we have actually two of them with LCD screens in front of them. At the top, we've installed the Raspbian distribution. At the bottom, Unikraft. We're going to power both of them on. It takes about 3 seconds to boot the GPU, and then the CPU and OS kicks in. You can see Unikraft is already booted, and Linux will take a while longer. Of course, it takes a while longer because it's doing a lot more things. It's initializing devices and so forth, but that's kind of the point. The point is that perhaps you don't need all those services and devices for your particular needs. To give you some performance numbers, we did a bunch of tests. Instead of, in terms of image size, we've built a number of Unikraft images. There's a Hello World baseline one that you can see on there, but also we have images that can run Lua or Nginx. An NPAC is a machine learning framework, SQLite, and WebAssembly. And we've compared that to Raspbian OS, another specialized Raspbian OS that we minimized, and Alpine Linux. And you can see we're talking roughly orders of magnitude difference, just to give you a rough understanding of what sort of levels of image sizes you can expect out of something that is specialized. In terms of power consumption, we again did measurements between Unikraft all the way on the right. So here we're just trying a dummy Hello World just to see what the power consumption is when roughly idling, versus the same thing on Alpine Linux, Raspbian, and a minimized Raspbian as well. And you can see on the bars, whether you're measuring amps or watts, we're getting sometimes up to 50% reduction. So that's also a nice gain. In terms of boot times, okay, you saw in the demo that Unikraft boots fairly quickly. Here it is more in numbers. You can imagine Alpine Linux in the range of a few seconds boot time. Versus different Unikraft images, whether it's running SQLite or Nginx, those boot times are in the order of tens of milliseconds or up to 100 milliseconds. One more metric, memory usage. This is how much the actual OS is using in terms of memory when it's running. Again, we're comparing it against Raspbian and Alpine Linux. And we're doing it against a bunch of different applications running on Unikraft, such as SQLite, Nginx, and Lua. And you can see, so the bars on the left for Linux, we don't have different applications because the application itself isn't consuming much memory. So most of the results are the same for the different applications anyways. And you can see for Linux, we're in the order of 20 to 40 megs. And for Unikraft, anywhere, certainly under a meg, and sometimes just hundreds of kilobytes. Of course, this is idle, as if you were to ramp up requests for Nginx, the memory consumption would go up, for instance. But all in all, you can see that there are gains to be had if you can specialize to the needs of your particular application. In terms of the tool and the ecosystem, as I mentioned, there's a menu. All of Unikraft is make-based. There's a lot of documentation on the website, and I'll post some links later on. And Unikraft has a build system that builds each library individually and then links them together. But you can also build an external library or application using their native build system, and then bring in the resulting library into Unikraft, into a Unikraft image. The selection of which platforms you want to use, architecture, and which libraries is done by a kconfig menu. If you've ever built a Linux kernel, you'd be familiar with this system. And then you can obviously save and restore configurations. In addition to that, we found that system, while there's a menu, and we found kconfig sometimes a little bit cumbersome, especially for people who just want to get started quickly. So we added a tool called Craft that is supposed to improve the user and developer experience, which is also open source. And there's a link to it on GitHub. And basically the way it works is, in order to build your specialized image, you start by just running a Craft update. So it's going to fetch all the information about what the libraries and applications that are available are. You can then type Craft list, and it's going to show you what all of these possibilities are: architectures, platforms, libraries, and applications at the bottom. And then you need to choose the application you want to use. You can choose your platform, for instance, bare metal ARM64 or x86 KVM. Then you can ask it to build your image. And then in the end, you can tell it to run for a specific platform. And then it'll actually run the application you want to run. So this should make it easy to get started. For those of you who know what unikernels are, normally this is a much simpler process than the expert work that would be needed to run unikernel projects in the past. So in terms of application and language support, we have an initial set of ported applications and libraries, things like web servers such as Nginx and LightDPD, databases such as Memcached is not quite ready, but there's Redis and SQLite. There's machine learning frameworks such as PyTorch and TensorFlow Lite. This might be important because machine learning is increasingly used on embedded devices. There's network processing frameworks such as DPDK and Click, and lots of languages, as I already mentioned. And this is just a screenshot to show you what it looks like. This is SQLite running, in this case, as a Zen virtual machine in just hundreds of kilobytes, and just running some inserts, some queries, and then that's it. In terms of future work and challenges, one of the things, if we're running bare metal, is obviously driver support. So what we're aiming to do is add some sort of compatibility layer so that we can reuse existing drivers from a common general purpose OS. This could be probably FreeBSD. And also device support. As I mentioned, we can now run on the Raspberry Pi 3 and also on this AVNet, the Xilinx Ultra 96 V2. And we're looking into some other boards like the Pine 64, and a question to the community might be, where should we go? Should we keep adding support for 96 boards? What are things that are important? Unikraft is an open source Linux Foundation project. It's got a BSD license, so it should be fairly friendly to both to people who want to just do research or try it out, or those who want to use it commercially. There's lots of information at unikraft.org, documentation on how to use it, how to get started, if you want to contribute to it. All the sources are on GitHub, so you can go to github.com/unikraft, and you can get a lot of pointers on there. The craft tool, as I mentioned, is also on GitHub. And there's also a mailing list in case you want to get in touch with us and contribute. And that's my last slide. So thanks a lot for your time, and I'm on the Slack channel if you have any questions. Thanks a lot.